Hey guys, this is a video on solving ordinary differential equations using Laplace transforms. Now for simplicity, I've created three main types of problems based on their roots. So in this video, I will be solving an example that has multiple real unique roots. So let's go ahead and get started. The first thing I notice about this expression is that we are already in the Laplace domain because we have everything in terms of s. And the second thing I notice is that our expression is already in both proper and normal form. Now, if you have any questions about how to determine if an expression is in proper and or normal form, I have another video that is just an overview of this entire topic, so go watch that video. Okay, so to actually solve this problem, the first step is going to be to determine the type or types of roots. So I'm going to go ahead and rewrite my denominator as such, because now it's a lot easier to see that we have one root at s equals 0, we have another root at s equals -2, and we have a third root at s equals -3. So for this expression, we have three real unique roots. The second part is to perform expansion. So I'm going to start with 4 over s times s plus 2 times s plus 3. And I'm going to set this equal to a specific right-hand side. So I'm going to make the denominator of my first term s. I'm going to make the denominator of my second term equal to s plus 2. And the third denominator is going to be equal to s plus 3. And then I'm just going to pick arbitrary letters to represent the values of these numerators. And this right here is what we refer to as partial fraction expansion. Okay, so at this point we want to find a common denominator for the right-hand side. So aka the characteristic polynomial. Now this guy right here is my characteristic polynomial, which is also the same thing that we have here. So basically I want to multiply each of these three fraction terms by something over something so that the denominators are all the same. So for my first fraction, I'm going to multiply by quantity s plus 2 times quantity s plus 3. For my second fraction term, I'm going to multiply by s times s plus 3 and for my third term, I'm going to multiply by s times s plus 2. Now I can take and combine all of the numerators on the right-hand side because they all have a common denominator now. And now both my left-hand side and my right-hand side also have the same denominator. So that means I can set the numerators equal to each other. And I'm going to go ahead and expand this out further. I don't know what that is. That is not an S. Okay, so now at this point we can move on to step 4, which is equating the coefficients of S. And I'm going to go ahead and move on to a blank slide for this. So on the previous slide we had the following. And what I usually like to do at this point is add 0 coefficient terms on the left-hand side so that I have all of my power terms match up. That kind of sounds confusing. I'll just go ahead and write it out. So I'm going to add a 0s squared and a 0s here to the left-hand side. Because for step 4, which is equating coefficients of S, I'm going to have S squared terms, S terms, and 0th order terms. So for my S squared terms on the left-hand side, I can more clearly now see that I have 0. And on the right-hand side, I have A, B, and C. For my S terms, on my right-hand side, I have 0. Or sorry, on my left-hand side, I have 0. And on the right-hand side, I have 5AS, 3BS, and 2CS. That is the wrong spot. There we go. Okay, and then for my 0th order terms, I have 4 on the left-hand side, and I have 6A on the right-hand side. So now I'm going to move on to step 5. which is solving for residues. So I'm going to go ahead and solve this expression. I'm going to get that a equals 4 over 6, which is the same thing as 2 over 3. And now I can take and substitute this value for a back into my other two expressions. So for my s squared terms, I can get 0 equals 2/3 plus b plus c. And at this point, I can go ahead and solve this equation for b. So I get negative 2/3 minus c equals b. And then I can also take and write 0 equals 5 times 2/3 plus 3b plus c. And I can take this expression for b and substitute it in here. And that gives me 0 equals 10/3 plus 3 times negative 2/3 minus c. Did I drop a 2 somewhere? I did. Oopsies. There should be a 2 here. Okay. That looks better. Okay, so now I can take this and substitute it back into this equation to solve for b. So that's negative 2/3 minus 4/3 equals b, which means that b equals negative 2. So at this point, we have solved for the residues, and we can move on to step 6, which is to substitute these values back into our partial fraction expansion, and then take the inverse Laplace transform. So I'm going to move to a clean slide. Okay, so if you remember from a couple steps ago, our partial fraction expansion was this. And in our last step, we solved for the values of a, b, and c. So that gives us x of s equals 2/3 over s plus negative 2 over s plus 2 plus 4/3 over s plus 3. And at this point, we can go to the Laplace tables. I use the one from my book when I took this class. You can pretty much use any one-sided Laplace transform you want. Like, there's a ton on Google. So find yourself a good Laplace transform table, and you'll see that if we pull out the 2/3 from this term, we will see in our table that we have something that looks like this. And converting from the Laplace domain to the time domain, we get 2/3. For this term, if we again pull out the 2 because it's just a constant, then we'll see that we have something that looks like this in our Laplace table. And that becomes -2 times e to the -2t. And last but not least, pull the 4/3 out of this term, and we should see something of this form in our Laplace table. And so converting back to the time domain, we get 4/3 e to -3t. And therefore, our complete solution in the time domain is x of t equals 2/3 minus 2e to the -2t plus 4/3 e to the -3t, all multiplied by u of t. And the u of t is because we are using one-sided Laplace transforms. If you have more questions on why I multiplied my complete solution by u of t, you can refer to my overview video on this topic, because I go into a lot more detail and I have some really pretty graphs to try and help you understand that better. But for this problem, this is our answer. So I hope this video helped you guys better understand how to solve an ordinary differential equation using Laplace transforms.